Okay, so we're going to solve the two-body problem here. Thus far, we've been treating the sun as fixed, but of course it does move a little bit under the influence of the Earth's gravity. Now, this is a closed system, so its center of mass will actually remain at rest. We could find the center of mass. We'll measure from the sun a distance big R, from the Earth a distance little r, little script r. Of course, the two of them together must add up to the total separation distance big R, which is what we've been working with here, right? We call this normal R. That's the sum of those two. So, measuring from the sun, the distance big R to the center of mass is given by this ratio. So we've got the mass of the Earth, m, at a distance r away, divided by the sum of the masses. So that would be how to find the distance big R. To find the distance script r measured from the Earth, we would say we've got the mass of the sun, big M, at a distance little r away, and we would divide by the sum of the masses. That's a little m. And so that's how we would find the distance script r. Now, of course, the center of mass is the balance point. So it must be, if you look at the diagram here, that big M times big R must equal little m times little script r. Okay, so those three equations define the center of mass. Now, if we look at the force equations of our planet relative to the center of mass, and we're going to see later on that the center of mass for the Earth-Sun system is really, really close to the center of the Sun. So we're talking about a very small change in what we had earlier. But the force equations will read as follows. You will have the mass of the planet times the acceleration in terms of this new variable r, so that's mass times acceleration, and that's got to equal the inwards force of gravity, which is gmm over the total distance squared, which is the sum of those two, script r plus big R all squared. Now, as well, the angular equation will tell us that r squared theta dot is h, is a constant. So those are the force equations relative to the distance script r from the center of mass. So there it is, r is the distance from the center of mass. Now, what we want to do is we want to try and write this just in terms of the variable script r. So we want to eliminate big R. We can do that using the balance condition that we had earlier. So it must be true, then we can say that big R will equal little m script r over big M. And so over here, where we had negative gmm over this sum squared, we can write that as negative g big M little m over script r plus m over big M script r all squared, which we can then pull out the script r squared, and we're left with 1 plus little m over big M squared, which will give us a big M over a big M plus a little m all squared. So now, if we put that back into our differential equation, then what we get is the following. We will have the mass times acceleration that we had earlier equals this new expression here that we just arrived at for the force. Now this is really close to what we had earlier, except for this extra factor here of big M over big M plus little m squared. So because the differential equation is essentially the same, we're going to get exactly the same format for the solution. I.e., we're going to have here 1 over script r equals a cos theta plus b. The only difference is a and b aren't going to be the same as before. B is going to be changed, right? Instead of just big M, we've got big M times this ratio squared. So B will look like this. Now the angular momentum variable is going to change as well, because H is going to be expressed in terms of this script r squared, or in terms of r naught v naught, if you use theta dot is omega over r. Or sorry, theta dot is omega, is of course v naught over r naught. That's not quite right. Let's use the correct variables. Theta dot is omega, and I'm going to say that's v naught over my script r naught. And so that's how you would express it in this form here. Oh, but hang on, that's totally wrong. Sorry, delete, 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 because it's not, I'm getting ahead of myself here. Theta dot is omega, it's v naught over script r naught. That's what I'm trying to say. Then if you square it and simplify, you'll get this expression here. Now, what is this script v naught? Well, it's the velocity of the Earth relative to the center of mass. Now, this is going to be less than the velocity of the Earth relative to the Sun, which is what we were expressing earlier as v naught. But again, there's going to be a ratio that governs them, okay? Because the rotational velocity of the Earth around the Sun turns out to be the same as the rotational velocity of the Earth around its center of mass, the same omega. And since omega is v over r, we have that v naught over the total distance. Oh, let me clear that. Just to be clear, this is Earth, Sun. No curvature there at all. So this over the total distance will equal this value of the Earth's speed relative to the center of mass divided by r. Now, we can again eliminate big R there. Let's see, is that coming up here? Okay, I'm about to do that. Because, of course, big R is little m script r over big M. And then I can rearrange this and okay, we'll pull out the script r, and then we're going to have 1 plus little m over big M, and this is v naught over script r, so the script r cancels, and if we rearrange this, put it over a common denominator, it will be big M over big M plus little m times the velocity of the Earth relative to Sun. And this is how we'll find the velocity of the Earth relative to its center of mass. Because, of course, what we measure is we measure the velocity of the Earth relative to Sun. Okay, so that's how we'll boost that into center of mass coordinates. So if you look at the B constant then, in this two-body problem, we see that there's a change in the mass term, of course, but there's also a change in the angular momentum term. So just to summarize then, there's a change in the mass term. There's an extra factor here that looks like this. And that just arises from the motion of the sun and the need to account for the change in distance from the center of mass. And then here we would have r naught squared. Let's try that again. Because there's so many r's and v's, I need to be careful about how I write them. Okay, so there's the mass term. And now h we said was r naught and then v naught, both of those squared. But we've just seen that this is the velocity of the Earth relative to the center of mass. We can substitute in there using this expression over here to see what sort of expression we have involving the velocity of the Earth relative to the sun. So you can see we're going to get, and again, this is Earth, sun. This one here is Earth, center of mass. And we're going to have the same mass term affecting the numerator as we are the denominator, so it's going to cancel out. And as a result, we end up almost with the same expression we had earlier for the b constant, except this r naught is smaller because this just measures the distance of the Earth from the center of mass. Earlier, we would have had just a normal r there, r naught v naught squared. So the differential equation is similar, but the b constant ends up a little bit different. Now, for the a constant, of course, we would need to substitute in. Okay, so our differential equation is 1 over r equals a cos theta plus b. We could plug in 0 angle, and then at 0 angle, it's going to be 1 over, and we'll make that, of course, the perigee as we usually do, a cosine of 0, which is just 1, so that's a, plus the b constant. So solving for a, you get 1 over the initial radius minus b, as we've done before, except now the b is different. And now this is just the distance of the Earth from the center of mass. Not much difference for the Earth-Sun problem. Now, interestingly enough, having got this value, this is the distance that the Earth is from the center of mass, we can also calculate the distance that the Sun is from the center of mass, again, just using the balance condition. And we find little m over big M times the Earth's path. So because this is an ellipse, it turns out that big R is an ellipse as well, i.e. the Sun also moves in an ellipse. So I wish I could write on here. Here you've got the Earth. Maybe I'll just draw it over here, and then you can add a few things on to your picture there. Microsoft Word sabotages this for Apple users, unfortunately. Okay, so what I would do is I would put the center of mass right about there. That's the center of mass. And then the Earth is out here going around on its ellipse, right over here, exactly opposite, because of course the center of mass has to lie on the line connecting them, is the Sun doing its ellipse around the center of mass. And as the Earth moves around like this, the Sun follows it around on its ellipse, so that they're always on a line. The line connecting them always passes through the center of mass. Now, also because R, big R, is proportional to this script r, it turns out that when little r is at its smallest, i.e. when we are at perigee for the Earth, big R is its smallest, so the Sun is at perigee at the same time as well. And way over here, when the Earth is at apogee, then the Sun way over here will be at apogee as well. So this is a very nice result. It means both of these things are doing ellipses. Now, it turns out that if you work it out, the Sun's ellipse is quite small. We're going to leave it for you to try this example. Okay. First of all, take this to be pretend the Sun doesn't move at all, and then just solve the problem and get this equation for the orbit. It's quite straightforward. Then find out where the actual center of mass is using our center of mass relationships. And they are summarized, let's see, where is it? Over here for you? Nope. Yes, over here. Here are your center of mass relationships. So use those to figure out where the Earth's sun center of mass is and show that you're basically inside the sun. Well, the sun is like 700 million meters of radius, and the center of mass is only 450 kilometers from the center. So clearly you're well within the sun. Then shift into center of mass coordinates and show that this is how far the Earth is from the center of mass, and this is how fast it's going relative to the center of mass, given this speed relative to the sun. So you could see that pretty much we're still at those same two values. Then find the Earth's ellipse around the center of mass, and that just involves using these initial values and then substituting into the equation that we have here using the B constant right here. This is the B constant for the two-body problem. Okay, so you first find R naught and V naught, and then find the B, and then you can find the A. So that'll give you the equation for the Earth's ellipse, and then this is the answer that you should find. You could take the ratio of those two and find the eccentricity, and then just put in theta is pi and find the apogee distance. That's how far the Earth is from the center of mass way over here. Then just use the ratio, which is given right here, to find the size of the sun's ellipse. And you should show that this equation is true. And then you could put in theta is 0 and pi and find out how far the sun is from the center of mass at those 2 points. Take the ratio and get the eccentricity. Not surprising, because big R and little r in direct proportion, you will find that the same eccentricity for the sun's ellipse as it is for the Earth's ellipse. And you have completely solved then the two-body problem. Okay, so then once you've got that solved, then of course we started our class here with two results, Kepler's third law, and we had arrived at a result for the period and related it to the A value, which is the length of the major axis of the ellipse. Well, the derivation doesn't refer to anything to do with the two-body problem until the very last line, because that's where we actually need to use the value of the B constant. So here's the new value of the B constant in our two-body problem. So we're just going to substitute in for BH squared here and get the new equation for the period in the two-body problem. And let's see what we get. So if you put in BH squared there, so you're still going to have 4 pi squared in the numerator. BH squared, you can see, is G big M. That's what it was before. And then we get this ratio, but I'm going to, let's see, invert it. So this will be M, and this will be M plus big M squared, and then it's again times A cubed. So we've got essentially the same result for the period that we have before. Before it was just 4 pi squared gm over A cubed, but then we've got this other factor here, which we've seen comes up in the two-body problem. So there's a slight modification for Kepler's third law in the two-body problem. Again, because big M is so very much bigger than little m in the case of the Earth, really there's just a very tiny effect on the period. Okay, little a continues as it was to be related to the length of the semi-major axis, but here, of course, we're now dealing in center of mass coordinates. Now, the derivation of the energy equation is quite a bit more work. For one thing, now not only is the Earth going to have energy, but the sun's going to have energy as well because it's moving. And so you end up with a similar equation, but again, we've got this m over m plus m ratio. This time it ends up to the third power. And you can see that because of the big M squared here, and this factor was accompanying big M before, you could kind of understand if it was 4 powers of this ratio, but it actually ends up being 3 because one of them cancels out in the derivation. It's not an especially pleasant derivation. So, if you want to work your way through it, it's really just 2 pages of algebra. But I'm going to show you next week an easier way to come up with these relationships. But for now, here they are all summarized. So this is what we had last time. There's the equation of the orbit. And there's B and A in terms of the initial condition, definition of eccentricity, angular momentum, and energy conservation. And then our class for this time, we started off with Kepler's third law. Period squared is semi-major axis cubed. Or sorry, half the semi-major axis cubed, the A constant. And then in the two-body problem, that's how you find the center of mass. There's the Earth's motion relative to the center of mass. There's the new value of the B constant. There's the angular momentum constant relative to the center of mass. That's how to boost into the center of mass system and find the velocity relative to the center of mass. Here's the new period relationship. Here's the new energy relationship. We have solved the two-body problem.